Today we cover week 9, and week 9 discusses electric fields in material space. And as I mentioned earlier, we have been dealing with the electric fields in a vacuum or in free space. And to start us off, we're going to look at the introduction, properties of materials, convection and conduction currents, and then we're going to look at conductors, polarization, and electric constant and strength. That is the subject of our material today, and let's go. So just before we go on, it's good to borrow a few items from the professor, and he gives us an important point that says that knowledge will forever govern ignorance. People who mean to be their own governors must arm themselves with the power which the knowledge gives. So, as I have mentioned in this chapter, we consider electrostatic fields in free space, or rather, in the last chapter, we considered electrostatic fields in free space, or space that has no materials in it. And thus, we have developed so far under electrostatics, what we have developed may be regarded as the vacuum field theory. By the same token, what we shall develop in this chapter may be regarded as the theory of electric phenomena in material space. So as will soon be evident, most of the formulas derived in the chapter 4 are still applicable, though some may require slight modification. Just as electric fields can exist in free space, they can also exist in material media, and materials are broadly classified as in terms of their electrical properties as conductors or non-conductors. And non-conducting materials are usually referred to as insulators or dielectrics. And those are two categories. All dielectrics are not insulators, and we will observe the difference as we carry on. A brief discussion of the electrical properties of materials in general will be given to provide a basis for understanding the concepts of conduction, electric current, and polarization. Further discussion will be on some properties of electric materials such as susceptibility, permittivity, linearity, isotropy, homogeneity, dielectric strength, and relaxation time. The concept of boundary conditions for electric fields existing in two different media will also be introduced. But for this class, I guess we will not cover all these. We are going to discuss the general concepts of materials at this point, and then these are the concepts that are going to be discussed in later lectures. So to start with, we are going to start with the concept of properties of materials. And we are going to say that a discussion of electrical materials may seem out of place in a text of this kind, but questions such as why an electron does not leave a conductor surface, why current carrying wire remains uncharged, why materials behave differently in an electric field, and why waves travel with less speed in conductors than in dielectrics are less or are easily answered by considering their electrical properties or the electrical properties of materials. Another discussion of this subject is usually found in other topics or in other texts such as those that cover physical electronics. So here a brief discussion will service to help us understand the mechanism by which materials influence an electric field. In a broad sense, materials may be classified in terms of their conductivity, which is measured in moles per meter, or more usually Siemens per meter, as conductors and non-conductors, or technically as metals and insulators, and sometimes we classify insulators as dielectrics. But each of the insulators have different properties that make them better dielectrics or poor dielectrics. So in a broad sense, we are saying that materials may be classified in terms of their conductivity, or that they may become conductors or non-conductors, and have brought in the table that we are referring to, that is table B1 from the appendices, and it classifies materials either as conductors, semiconductors, and insulators. And in addition, we are saying that the conductivity of material depends on temperature and frequency. And a material with high conductivity that is measured in sigma, and we say that when sigma is far much greater than 1, it is referred to as a metal, whereas when the conductivity is far much less than 1, that material is said to be an insulator. A material whose conductivity lies somewhere between those of metals and those of insulators is called a semiconductor. And the value of conductivity of some common materials are shown in the table I've just shown you, table B1 in the appendix. And from that table, we are able to see the classification of metals, semiconductors, and insulators with their respective conductivities. From this table, it is clear that materials such as copper and aluminium are metals. Silicon and germanium are semiconductors, and glass and rubber are insulators. So that is definitely very well seen at this point, that here we have our semiconductors. Here we have silver and copper as very good, and aluminium as very good conductors. And we have water, glass, paper amongst the insulators. So having said that, we can say that the conductivity of metals generally increases with the increase in temperature, that is in general, and at temperatures near absolute zero, some conductors exhibit infinite conductivity, and they are called semiconductors. And the examples of that is lead and aluminium. The conductivity of lead at 4 kelvins is of the order 10 to the power 20 Siemens per meter. And if you are interested, you can read some further literature that is indicated by this or down here. You can look at this one. Now we shall be concerned only with metals and insulators in this text or in this series of lectures. And microscopically, the major difference between a metal and an insulator lies in the number of electrons available for conduction of current. We normally say that dielectric materials have few electrons available for conduction of current, whereas metals have an abundance of free electrons. Further discussion on the behavior of conductors and electrics in an electric field will be given in the subsequent sections. So for now, we are going to start with convection and conduction current. So to start with, we are going to discuss the concept of electric current. And to do that, we are saying now that electric voltage, which is also referred to as the potential difference, and the current are the two fundamental quantities in electrical engineering. There are two fundamental quantities in electrical engineering. We have already considered the potential in the last chapter. And before we examine how the electric field behaves in a conductor or a dielectric, it is appropriate that we consider the concept of current or electric current. And generally, we define the electric current as the motion of electric charges. And the formal definition of current states that the current which is measured in amperes through a given area is the electric charge passing through the area per unit time. And equation 5.1 defines exactly that. The rate of change of Q and or gives you the current that is flowing through that unit area. Thus, in a current of 1 ampere, charge is being transferred at a rate of 1 coulomb per second. So you can actually express current in coulombs per second, which is equal to 1 ampere. We now introduce the concept of current density, and we say that if a current delta I, or an elemental fraction of current, flows through a planar surface, and a planar surface is just a surface on a plane. We are saying that this is my elemental surface that we can describe to have the area delta S. If this an elemental current delta I flows through this surface, then we define current density as the amount of current that is flowing delta I divided by delta S to be equals to J, and J is the current density. And equation 5.1 may be modified to express the elemental current in terms of current density, where we say that, of course, we have said delta or J is equal to delta I over delta S. Therefore, we can make S this the subject of the formula, and we end up by having J delta S to be equivalent to the elemental current that is flowing through a unit area. And for that to be true, we assume that the current density is perpendicular to the surface. So we are saying here is our surface, the elemental current is flowing in that direction. This is my elemental current, and this is my elemental surface. Therefore, we assume that the angle that the elemental surface makes with the current is actually equals to 90 degrees. Therefore, that applies. However, if it is not making the 90 degrees between the elemental surface and the elemental current, that means we are going to use the dot product to express the product between these two. And this, as you remember, can be expressed as J delta S. Now they are not vectors, then you say cos theta, where theta is the angle between them. Is the angle between them. Just to clarify this concept further, I will make this quick illustration that says that if this surface is a vector, then it has the scalar and the AS component. And remember here, I think I should have just said what is coming out on this side is the current, or the elemental current, but the elemental of the surface electric current density is therefore pointing normal, or if when we have said when it is not normal to the surface, it is making an angle with the surface. So remember that the surface, when it is drawn like that, it always has a unit vector pointing normal to the surface, and that is how we normally indicate AS. And for that reason, J, we have said it should always be normal to the surface, and that will mean that if it is normal, it will be parallel to the AS. And therefore, when it is parallel to the AS, the AJ unit vector and AS unit vector will give you a 1. However, when the AJ is making an angle like that, making an angle theta with the AS unit vector, then that is when this equation comes in about. Therefore, for just to clarify, when theta is equals to 0, that means the current density is normal to the surface, and the cos of 0 will be 1, and therefore this will be able to start. If it doesn't start or doesn't work because it is not normal, that means we are going to factor in the angle theta that will be expressed as in equation 5(4). So to sum it up, we mentioned that depending on how I is produced, there are different kinds of current densities. The convection, the convection current density, the conduction current density, and the displacement current density. For this section, we shall deal with the convection and the conduction current densities, and the displacement current density will be discussed in chapter 9, which I believe will be covered in electromagnetics 3. So for now, we are going to dwell with the first two, the convection and the conduction current densities. And we also note that equation 5(4) applies to any kind of current density, and therefore becomes very useful in our illustrations. And now we quickly discuss the convection current, and we say that as distinct from conduction current, the convection current does not involve conductors and consequently does not satisfy the Ohm's law. It occurs when current flows through an insulating medium such as a liquid, rarefied gas, or a vacuum. And we consider an example of beam of electrons in a vacuum tube, which consists of a convection current. And in such a tube as shown in this figure 5.1, if there is a flow of charge of density rho v at a velocity u in the direction of y, then from equation 5(1) that said that elemental current is defined by its change, the flow of charge per unit time. Therefore, we can be able to calculate charge to be given by rho v times the surface, and we are saying that it is flowing at the velocity u, which can be quantified as change in y over change in time. So we define a new equation that says that the current flowing due to the convection current can be defined by rho v change in the elemental surface area delta S times the velocity of row of those charges uy. And we make a new definition which is similar to what we have said already, that says the current density at a given point is the current through a unit normal area at that point. And in this case, the y-directed current density, Jy, is simply going to be given by the current flowing in that direction, which we have seen to be this. You divide by the surface over which, or the surface area over which the current is flowing, which is ds. And if you divide here by ds, you actually get rho v uy. And therefore, in general, we make a conclusion that the current density can always be given by rho v u, and u is the velocity of charge. We are saying now that, and of course, you can see that this is given in a scalar, and the unit vector a u pointing in the velocity of the charge. The current I is the convection current, and J is the convection current density measured in amperes per square meter squared. The conduction current requires a conductor. A conductor is characterized by a large number of free electrons. And therefore, when the free electrons are inside an impressed electric field, they're going to move. When an electron field E is applied, then that is the force that acts on these charges. And we can characterize that force as E acting on small e, as depicted in equation 5.8. Since the electron is not in free space, they are not going to experience an average acceleration under the influence of electric field. Rather, they suffer from constant collisions with the atomic lattice, and these collisions drift from one atom to another. If an electron with mass m is moving in an electric field E with an average drift velocity u, then according to Newton's law, we say that the average change in momentum of the free electron must match the applied force. So we are saying that the average change in momentum of the free electron, which is defined by mass times the velocity of the atom, the average change is going to be over time. So the rate of change of the momentum of free electrons must be equivalent to the force that the electrons are experiencing due to the electric field E. If we want to make U the velocity, the subject of the formula, we can just bring the m and the tau on this side, and we end up with equation 5.9b as such. And what that tells us is that, of course, tau is the average time interval between collisions, which is characterizing the average change of momentum of the free electrons. And we are saying that this equation 5.9 indicates that the drift velocity of the electrons is directly proportional to the applied field. So we are saying that this is the constant of proportionality. If there are n electrons per unit volume, then we will define electronic charge density to be the number of electrons per unit volume. and we define that as in equation 510. The number of electrons, and each electron has charge E. And therefore, the conduction current density will be characterized by the electron charge density multiplied by the average or the drift velocity of the electrons. And since we have been able to define U in equation 5.9b, and we have defined rho V in equation 5.10, then we can be able to say that we get this value that is equivalent to the conductivity of the conductor. And we get equation 5.11 that says that the current density is equivalent to the conductivity of the medium times the applied electric field. And we say that this relationship is called the point form of the Ohm's law.